Good morning everyone. My name is Rohit from BSc Chemistry Honors second year. Today's my topic is chemistry of lanthanoid elements from Pardeep's Inorganic Chemistry book. Lanthanides are the elements present in period 6 of the periodic table with atomic number 57 to 71. Since the last electron in the atoms of these elements enter the 4f orbital, therefore these elements constitute what is known as f block elements. These elements are also named as inner transition elements. This is because these elements constitute a transition series within the third transition series. More precisely, the 5D transition series. These elements are located in first row of elements kept at the base of the periodic table. The first element of the series is named lanthanum, and a group of 14 electrons following lanthanum is called lanthanides. In other words, elements starting from cerium and ending with lutetium are known as lanthanides. The name lanthanides was wrongly coined as the ending "ide." More correctly means a negative ion, such as oxide or chloride ions. For a few years, IUPAC suggested a new name, lanthanons, instead of lanthanides to these elements. However, it was also disapproved soon because the ending "on" is preferred for non-metals, whereas the lanthanides are all typical metallic elements. IUPAC has finally approved these elements to be named as lanthanoids, with occurring in very small amounts. However, nowadays the term rare earth elements is itself misleading because many of these elements have been found to be abundantly available. For example, cerium is as abundantly available as copper. Huge deposits of these elements have been located in USA, Scandinavia, and India. Electron structure and position of lanthanides in the periodic table. As already discussed, lanthanides involve the gradual filling of 4f orbitals. The ground state electronic configuration of each lanthanide is occupied by the outermost cell by the two 6s electrons. Since the energy of 6s, 5d and 4f are similar, the order of filling the 4f orbitals may show some irregularities. It is found that at lanthanum, the incoming electron enters the 5d subcell and therefore it has the following electronic configuration. However, as we move onward after lanthanum, the energy of 4f subcell becomes distinctly lower than the 5d subcell. As a result, the next electron in cerium enters the 4f subcell. The electronic configuration of cerium is represented as the fitting of 4f subcell continues till one reaches ytterbium, which has the electronic configuration. 4f block elements may be defined as those elements in which the last electrons enter the anti-penultimate energy level. Since both the 6s and 4f orbitals have been completely filled, the next electron has no choice but to go to the 5d orbital. In lutetium, the electron enter the 5d orbital and the electronic configuration is as following. It is important to note that the electronic configuration of the penultimate cell is invariable sp2 s2p6 except for three elements, which is lanthanum, gadolinium, and lutetium. It is equally important to note that the 4f orbitals are unoccupied in case of lanthanum. 4f orbitals are half filled in case of gadolinium, and 4f orbitals are completely filled in lutetium. General characteristics of lanthanides. The general electronic configuration of the lanthanides may be represented as lanthanides 4f 0 to 14, 5d 0 to 1, 6s2. The ground state electronic configuration of the outer cells of lanthanide atoms are given in table 4.1 as following. Physical constant of lanthanides. Some of the important physical constants of lanthanides are given in table 4.2. Ionization energies. Lanthanides have low ionization energies. The first and second ionization energies of the lanthanides increase in general, but will show little variation with atomic number across the lanthanide series. The trend is less clear for first ionization energy than for the sum of the three ionizations. It is clear from the figure 4.1. The deviations are observed only for EU, GD and YB LU, which involves the half-filled and completely filled f orbitals. The first ionization energy of the lanthanides roughly corresponds to 550 kJ mole inverse, whereas the second ionization energy corresponds to 1150 kJ mole inverse. These values are comparable to calcium, which has the first and second ionization energy values of the order of 590 kJ mole inverse and 1150 kJ mole inverse respectively. Here is the table 4.2. Melting and boiling points. The melting point of any substance reflects the force of attraction between the atoms, molecules or ions that, that compose the solid. An inspection of the table 4.2 reveals that lanthanides possess high melting and boiling points. However, the melting and boiling, especially the boiling points of lanthanides, do not show any regular trend across the lanthanide series. The properties of the lanthanide strongly suggest that three valency electrons per atom are involved in the metallic bond. The 4f electrons are not involved in metallic bonding, as these are located on the individual atoms and are well shielded from each other. The most clear-cut anomalies in the lanthanides are provided by europium and ytterbium, which behave much as would be expected of deviant metal, indicating less than 3 electrons per atom involved in metallic bonding. These are also the two lanthanides which most readily form deviant ions in the compounds. In addition, these two ions have half-filled and completely filled 4f subshell respectively. This explains the low melting points in case of europium and ytterbium as compared to the values for the other lanthanide elements. Density. The densities of the lanthanides do not display a regular trend across the lanthanide series. Both europium, EU and ytterbium YB has unusual low densities. Heat of fusion and heat vaporization. The amount of heat required to convert a substance from a solid at its melting point to a liquid is called heat of fusion, whereas the amount of heat required to convert a substance from a liquid at its boiling point to a gas is called the heat of vaporization. In both the cases, the energy required is used to overcome the attractive forces. In case of lanthanides, the heat of fusion and heat of vaporization do not show a regular trend across the lanthanide series. Electronegativity values. Pauling defined electronegativity as the power of an atom in a molecule to attract electrons toward itself. The lanthanides show the lower Pauling electronegativity values between 1.0 to 1.15. These values are very close to those of alkali metal and alkaline earth metals. Since the electronegativity value of lanthanides are almost same as that of S block elements, it is anticipated that lanthanides form ionic compounds. Oxidation states. Oxidation state of plus 3 is shown by all these elements and in most cases is the most stable oxidation state. Some of the lanthanides in addition to plus 3 show plus 2 and plus 4 oxidation states as well. However, plus 2 and plus 4 oxidation states are always less stable than the plus 3 state. The reason for the unusual oxidation state of plus 2 and plus 4 can be attributed to the extra stability associated with FO and F7 half-filled and F14 completely filled electronic configuration. Examples giving various oxidation states are given below. Plus 3 oxidation state: lanthanum, gadolinium and lutetium. distinctly display +3 oxidation state. This is because after the loss of three outermost electrons, these elements acquire the stable configuration of empty, half-filled and completely filled 4f subcell as shown in table 4.3. +4 oxidation state. The most stable oxidation state of cerium is +4. This is because after the loss of 4 electrons, cerium acquires the outer electronic structure as F naught, D naught, S naught, which corresponds to that of noble gas configuration. Similarly, terbium acquires the half-filled F7 subcell configuration. +2 oxidation state. The most stable oxidation state of europium is +2. This is because after the loss of 2 electrons, europium acquires the outer electronic configuration of half-filled F7 subcell configuration. Similarly, ytterbium acquires the outer electronic configuration of completely filled F14 subcell configuration. The outer electronic configuration of various lanthanides in different oxidation states are given in table 4.3. Here's the table 4.3. There are instances where some of the lanthanides display +2 and +4 oxidation state, with white acquiring either F0, F7 or F14 configuration. For example, samarium and thulium show +2 oxidation state electron respectively, which are one electron short of the required half-filled or completely filled F14 configuration. Similarly, praseodymium and neodymium show +4 oxidation state with electronic configuration. The existence of such oxidation states, which cannot be explained on the basis of configuration, might be explained on the basis of occur factors and such as kinetic and thermodynamic factors. Magnetic properties. The magnetic properties in chemical compounds determine the presence of paired or unpaired electrons. If substances containing only spin paired electrons are placed in the magnetic field, these are repelled by the field. This phenomena is called dimagnetium. On the other hand, substances containing one or more unpaired electrons when placed in the magnetic field are attracted by the magnetic field. This phenomena is called paramagnetism. It is important to note that the attraction of each unpaired electron is many times stronger than the repulsion of all the spin paired electrons in that atom. Most of lanthanoid ions, with the exception of La3 positive, Lu3 positive, Ce4 positive, and Yb2 positive ions, are paramagnetic. The paramagnetism in the lanthanide ions arises because of the presence of unpaired electrons in their 4f subshell. The ions La3 positive, Lu3 positive, Ce4 positive, and Yb2 positive are diamagnetic because they have no unpaired electrons. The magnetic behavior of a substance is expressed in terms of the magnetic moment. The larger number of unpaired electrons, the higher is the magnetic moment. The magnetic moment arises from two of motion of electrons. The spinning of electrons on its own axis generates a magnetic moment called magnetic moment. Orbital motion of the electron around the nucleus also produces magnetic moments, which called orbital magnetic moment. The magnetic behavior in case of lanthanides arises due to contribution both spin magnetic movement as well as orbital magnetic behavior. This behavior of lanthanides is in contrast with the behavior of transition elements of d block, where the magnetic moment corresponds exclusively to spin only values. In case of transition elements, the d block elements orbital are not well shielded from the environment and interact strongly with the ligand surrounding the metal ion. Because of the electric field of the ligands, the orbital motion of the electron is restricted. That causes the orbital movement to decrease considerably. In other words, the orbital movement of the electrons in case of transition elements can be neglected. On the other hand, in case of the 4f subshell are well shielded from the surrounding and do not interact with the surrounding ligands. As a result, the orbital motion of the 4f orbitals is not restricted or quenched. Thus, the magnetic movement of the lanthanide ions arising due to both electron spin and orbital motion of the electron can be calculated from the expression where S is equal to total spin quantum number and L total orbital magnetic quantum number. Table 4.4 shows magnetic moments. This simple relationship works only for the lanthanides. Both La3 positive and Lu3 positive have no unpaired electrons and consequently both have zero magnetic moment values. However, the magnetic properties of the lanthanides are different from those of transition elements. If the lanthanides, the spin contribution S and orbital contribution L couple together to give a quantum number J. The new quantum number J can have two types of values. J is equal to L minus S when the orbital is less than half fill. J is equal to L plus S when the orbital is more than half full. Therefore, the magnetic moment values for the lanthanides in Bohr magneton is given by mu is equal to G under root J into J plus 1, where G is Landes splitting factor for the electron and is defined as the theoretical and experimental determined magnetic moment value of the tripositive lanthanide ions are given in table 4.4. It is clear from the table 4.4 that there is an excellent agreement between the theoretical and experimental values when the magnetic moments are calculated on the basis of spin and orbital contribution together. All the tripositive lanthanide ions expecting La3 positive and Lu3 positive contain unpaired electrons and are therefore paramagnetic. A plot of the magnetic values of tripositive lanthanide ions reveal that the magnetic moment values increases first up to neodymium and then decreases up to samarium. It increases steadily again and reaches a maximum value for dysprosium ion and then starts decreasing till it reaches zero value for lutetium ion, which is diamagnetic. It is important to remark that the high values of the magnetic moments for Tb3 positive and Dy3 positive clearly demonstrate the role of orbital contribution toward the magnetic moment of the lateral lanthanides. A distinct feature of the curve is its unusual shape. The unusual shape of the curve arises because when the F subshell is less than half filled, the spin and orbital magnetic moments work in opposite. But when the F subshell is more than half full, they work together. Here is an example. Color and spectral properties. Lanthanides in their elemental state are silvery white, while many lanthanides ions are distinctly colored, both in the solid state as well as in the aqueous solution. The color of the lanthanide ion depends primarily on the number of unpaired F electrons. The color of the lanthanide ion remains same even on changing the counter anion. Thus, color of the lanthanide ion is characteristics of the cation. It has been found that lanthanide ion containing NF electrons often have a similar color to those with F electrons. The color of the lanthanide ions can be grouped symmetrically and the trivalent gadolinium ion as shown in table 4.5. The color of the lanthanide ion is due primarily to the absorption of light from the visible region of the spectrum that results in the electronic transition within the 4F level. This type of transition is called FF transition. A unique feature of the spectra of transition lanthanide ion is that the absorption bands are sharp line like bands in the ultraviolet, visible or near infrared regions. This behavior is in contrast to the absorption bands of DD type transition metals, for example Ni2 positive and CO2 positive ions, which appear as bold absorption bands. The band of lanthanide ions are so sharp that they are used for characterizing lanthanides. The reason for very sharp absorption band is that the 4f orbitals are located deep inside the atom. Thus, they are effectively shielded from environmental factors such as the nature and number of ligands, which form the effectively shielded from complexes and from vibration of the ligands. A typical lanthanide ion spectrum of holmium is shown in figure 4.3. Thus, the color of the lanthanides ion does not change with the different ligands. In other words, the absorption band show little dependence on the nature of ligand. It is important to mention that this behavior is in contrast with transition elements where DD transition give absorption bands whose position change from ligand to ligand and width of the peak greatly broadened because of the vibration of the ligands. Vibration of the ligands change the external field. However, lanthanides in the plus 2 and plus 4 oxidation state with the same number of electrons do not have the same color as observed in case of lanthanides in the plus 3 oxidation state. Some of the typical isoelectronic lanthanides in the plus 2 and plus 4 are shown in table 4.6. Here's the table 4.6. Apart from FF transitions, sometimes the color of the lanthanide ions can also be attributed to FD transition. The FF absorption of lanthanides ions have low intensity because these transitions are not allowed. However, FD transitions are allowed. As a result, they show very intense absorption bands. For example, Ce3 positive and Tb3 positive show very intense absorption bands. Transitions due to FD bands are broad, in contrast to narrow FF bands. In addition to FF and FD transitions, the color of some of the lanthanide ions can be due to charge transfer. This transfer of charge occurs from the ligand to the metal. This is more probable if the metal is in high oxidation state of the ligand has strong reducing properties. Charge transfer unusually produce intense colors. For example, a strong yellow color of Ce4 positive solutions arises due to charge transfer rather than FF transitions. The blood red color of SM2 positive is also due to charge transfer. Ionic radii and lanthanide contraction. Covalent and ionic radii increases on moving down a group in the periodic table. This is due to the presence of additional shells between the successive periods. On the other hand, on moving from left to right across a period, the covalent and ionic radii decreases. This is attributed to the increased effective nuclear charge, as a consequence of which the outermost electrons are attracted more and more. This results in the outermost electrons being pulled more and more closer. We also know that the shielding effect of electrons decreases in order SPDF. The atomic and ionic radii of lanthanides are given in table 4.7. Here is the table 4.7. A careful inspection of the table 4.7 reveals that as we evolve along the lanthanoid series from lanthanum to lutetium, it is a gradual decrease in the size of the atoms and ions with the increase in atomic number. It has been observed that in case of tripositive lanthanide ions from Ce3 positive to Lu3 positive, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. This shows that the overall decreases of 0.17 angstroms across in occurs in going from Ce3 positive to Lu3 positive ion. This is indeed a very small decrease in comparison to elements of other groups and periods. The atomic radii of the elemental lanthanides also decreases from 1.83 Armstrong to 1.73 Armstrong. The total decrease of atomic radii from Ce to Lu comes out to be 0.10 Armstrong. This small steady decrease in atomic or ionic radii of lanthanoid elements with increase in atomic number is called lanthanoid contraction. Cause of lanthanoid contraction: the shapes of the orbitals account for the relative atomic radii of F block elements. The lanthanides involve the gradual filling of 4f orbitals. The lobes of the 4f orbitals occupy markedly different regions of space and are therefore far apart from each other. Consequently, f orbitals repel one another very weakly. Secondary, electron density in f orbital is low near the nucleus. As a result of being away from the nucleus, 4f orbitals are not very effective at shielding other electrons from the nucleus. Thus, with the increase in atomic number, the nuclear charge, the effective nuclear charge experienced by each 4f electron increases. This increases the inward pull of the 4f electrons and result in the reduction of the size of the atom of iron. This contraction in the size of the atom or ion by pulling the valence electrons inward due to high nuclear charge and the poor shielding effect of the f electrons is the main cause of what is called lanthanoid contraction. Consequences consequences of lanthanoid contraction. Some of the important consequences of lanthanoid contraction are given below. Steady decrease in size of lanthanoid ions. As a result of lanthanoid contraction, there is a gradual or steady decrease in the ion radii of lanthanides. Electronegativity. This is a slight increase in electronegativity of the trivalent ions. Electrode potential value E naught. There is a small but regular increase in the electrode potential value for the process. Resemblance of second and third transition series. The atomic radii of elements of second transition series period 5 are typically greater than those in the first transition series period 4. However, the radii of the third transition series elements period 6 are about the same size as the second transition series. There is a pronounced decrease in the atomic radii along the lanthanoid. When the d block resumes at lutetium, the atomic radius has fallen from 2.24 Armstrong for barium to 1.72 Armstrong for lanthanum. As a result of this, the atoms of all the following elements are smaller than expected. In brief, as a result of lanthanoid contraction, the chemistry of second and third transition series resemble each other more than the elements of first and second transition series. Difficulty in separation. Because of the very small change in the size of the lanthanide ions in the lanthanide series, their chemical properties are alike. This causes the separation of elements a difficult task. High density. The lanthanide's contraction is responsible for the high density of the elements of the transition series. A block of iridium, for example, contains as many as atoms as a block of rhodium of the same volume, but each iridium atom is nearly twice as heavy as each rhodium atom. Therefore, the density of iridium is nearly twice that of rhodium. Difference in basicity. The size of the lanthanide ion decreases regularly with increase in atomic number in the lanthanides. The decrease in the size of the cation tends to increase the covalent character according to Fajan's rule. As a result, the bonding of the smallest cation and the hydroxide ion becomes mostly covalent. In other words, the basic strength of the hydroxide decreases. This explains clearly that LaOH thrice is the strongest while LuOH thrice is the weakest base. Similarly, the hydroxide. There is also a decrease in the basic strength of oxides of lanthanides with increase in the atomic number. This decrease in basic strength of oxide and hydroxide of lanthanides with increased atomic number is also reflected in several other related properties. For example, hydrolysis of ions. Due to the decrease in the basic strength, there is a slight increase in the degree of hydrolysis in solution from La3 positive to Lu3 positive. It means La3 positive ions are less readily hydrolyzed than the Lu3 positive ion. Solubility of the salts. Hydroxides of lanthanides precipitate with decreasing pH value from the nitrates of La3 positive to Lu3 positive at 20 degrees Celsius. For example, La3 positive precipitates at pH 6.83, whereas Gd3 positive precipitates at pH 6.83, while Lu3 positive precipitates at pH 6.30. Thermal decomposition of oxysalts. The stability of the trinitrates of lanthanide decreases with the increase in atomic number. Thus, LaNO3 thrice, which is more basic, decomposes little, whereas LuNO3 whole thrice decomposes readily. Complex formation tendency of lanthanides. Compared to transition metals, lanthanide ions do not readily form complexes. It is primarily due to the large size of the ions, which result in the small charge of ionic radii ratio. Lanthanide ions form complexes preferably with fluorine and oxygen donor ligands. They form complexes with beta diketones such as acetic, acetyl acetone, oximes, ethyl ND, amine nitric acid, adta, and hydroxylic acid such as citric acid. The lanthanide elements are often 6 coordinated in complexes. However, higher coordination number are also known in some complexes. For example, 8 coordination is found in La2O2, where ACAC acetyl acetonate, as well as in the anionic species Y. The high charge density on Ce4 positive is expected to form stronger complexes than the tripositive ion. Ce4 positive has been found to form the diionic complexes in a non-aqueous medium N2O4. This is an interesting complex in which the coordination number of cerium is 12. Nitrate ion behaves as a bident ligand as shown in figure 4.6. Organometallic compounds. Lanthanides ion being highly electropositive do not form complexes with pi bonding ligands. The inability to form complexes is also due to the non-availability of f orbitals for bonding. However, lanthanides form two types of compounds: predominantly ionic cyclopentadienes, sigma bond alkyl aryls. The cyclopentadienes can be prepared by the reaction of anhydrous LnCl thrice and NaC5H5 in a polar solvent like tetrahydrofuran THF in appropriate molar ratio. Using this methodology, it is possible to prepare cyclopentadienes compounds of the type. In polar solvents, these complexes are highly solvated and monomeric in nature. However, in non-polar solvents, the tricompounds are insoluble while the bicompounds dimerize. The alkyl and aryl lanthanides can be prepared by the mathematical reactions either in ether or in the THF solutions. Occurrence of lanthanides. Lanthanides were originally named as rare earth or rare earth elements because they were believed to be rare. However, the term rare earth is misleading as these are actually fairly common now. The word earth was used because most of these elements occur as oxide, with the exception of promethium, which is radioactive. All the lanthanides occur naturally. Recent studies have revealed that some of the lanthanides, namely cerium, lanthanum, and nodium, occurs in fairly abundant quantities. It has been found that lanthanides with odd atomic numbers are less abundant than the lanthanides with even atomic number. Cerium has been found to be almost as abundant as copper. All the lanthanides excepting cerium and promethium are more abundant than iodine. The abundance of the lanthanide elements and the number of naturally occurring isotopes are given in table 4.9. A number of minerals A number of minerals containing lanthanides are also known. Some of important minerals are monazite. Monazite sand is the most important and widely spread mineral. It accounts for 78% of the mined lanthanides. It predominantly contains phosphates of lighter lanthanides, which is cerium, neodymium, praseodymium, together with small amounts of ytterbium, and the heavier lanthanides along with thorium phosphate. Monazite has been found to occur in Brazil, USSR, USA, southern India, and Malaysia. Bastenicite is a mixed fluorocarbonate with the formula M3 positive F, where M is Ce3 positive, La3 positive, Nd3 positive, and Pr3 positive. Bastenicite differs from monazite sands as it does not contain ytterbium and has a negligible small amount of thorium in it. Large deposits of the mineral bastenites are formed in Sweden and New Mexico. Cerite. The mineral cerite contains double silicates of Ce, La, Pr, Nd, and Sm along with aluminium and iron. Here's our topic ends. Thank you.